Hello everyone, I am Dr. Karthika from Department of Biomedical Engineering, SNS College of Technology, Coimbatore. Today we are going to discuss about Introduction to Fourier Transform in Biomedical Image Processing. Okay, I have a question for you. What is the use of this Fourier Transform in medical image processing? What is the necessity of Fourier Transform in image processing applications? Okay, let's move on to the topic first. What is Fourier series? Actually, any function that periodically repeats itself can be expressed as a sum of sines and cosines of different frequencies of each multiplied by a different coefficient is called Fourier series. See here the example. Here the function is periodically repeats itself and it can be expressed in terms of the sum of sines and cosines at different frequencies and which is multiplied by different coefficients. See here the sample Fourier series. I think you will get a clear idea about what is Fourier series. Okay, here notice how we get closer and closer to the original function as we add more and more frequencies. Because if the frequency is slow, we can get the wider one. Suppose if the frequencies are high, means we can get the closer frequencies and closer waveforms. See the animation. Okay, here frequency domain signal processing examples are expressed in terms of Excel. See the first one filtered signal and the second one filtered signal. Can you differentiate it? Okay. What is the use of this DFT? In Fourier transform, we have inverse Fourier transform. What is the necessity of this discrete Fourier transform? Normally, our waves are discrete. While converting analog to digital, discrete operation is the main element. So, this discrete Fourier transform and inverse Fourier transform are very important because Fourier transform we convert an image function into application oriented function with respect of Fourier transform. At the receiver side, we can get the Fourier transform output function with the help of inverse Fourier transform. Like that, we have DFT as well as inverse discrete Fourier transform, IDFT. Okay, what is the formula for this f of uv? F of uv, it is equal to summation x equal to 0 to m minus 1, summation y equal to 0 to n minus 1, f of xy of e power minus j 2 pi of ux by m plus vy by n. For u, it is equal to 0, 1 to up to m minus 1 and v, it is equal to 0, 1 to up to n minus 1. Okay. See here the DFT of the two-dimensional image. It can be visualized by showing the spectrum of the image component frequencies. First one is our two-dimensional image visualization and the second one is our DFT output. It shows the spectrum of image component with different frequencies. Okay. See here the input. It is expressed in XY two-dimensional image. And see here the output spectrum of intensities, it is expressed in UV. Okay, and we have some sample images. The first one is scanning electron microscope image of an integrated circuit magnified in 2500 times, and the output of DFT Fourier spectrum of the image. Okay, see the original image. See the spectrum of different frequencies of a 2D image. Okay, then we'll move on to the inverse DFT. If a DFT is processed in the input side, definitely we have to do inverse DFT in the output side. So what is the formula for this inverse DFT? Again, we use f of xy, it is equal to 1 by mn multiplied with summation u equal to 0 to m minus 1, summation v equal to 0 to n minus 1, f of uv multiplied with e power j 2 pi of ux by m plus vy by n. Here x equal to 0 to m minus 1 and y equal to 0 to n minus 1. Okay, and the DFT and image processing. What is the use of DFT in image processing? How do we relate DFT in image processing? Okay, first, to filter an image in the frequency domain, we use DFT process. Because with the help of filters only, we can get the highly enhanced error-free output in the output side. So, first step, we have to compute f of uv, the DFT of the image. Second, multiply f of uv by a filter function h of uv. See the block. And finally, compute the inverse DFT of the result. Before that, we have to do pre-processing in the input side and post-processing in the output side. Okay, and here we have some basic frequency domain filters. Here we have low pass filter, high pass filter. We know that low pass filter, which is mainly used to eliminate the high frequency components, and high pass filter, name itself says it eliminates low frequency components, and it is mainly used to pass the high frequency components only. Okay, some basic frequency domain filters. See the output of filter. See the output of low frequency filter, low pass filter, high pass filter output. Okay, what is the use of this filters in image processing? Where do we apply these filters? Okay, in smoothing frequency domain filters, we use g of u comma v and h of u v. What is the use of this g of u comma v and h of u comma v? What is the purpose of smoothing and sharpening? Actually, smoothing and sharpening are mainly used to eliminate the unwanted components in the image. Okay, here the basic model filtering is g of uv, it is equal to h of uv multiplied with f of uv, where f of uv is the Fourier transform of the image being filtered and h of uv is the filter transform function. Here we have the low pass filters as well as high pass filters. Low pass filters only pass the low frequencies, drop the high ones, and vice versa for high pass filters. Thank you.